Hello everybody and welcome to video lecture on operations research, and we are now in the notes linear programming with SPICE and chapter 8, that is called duality. We still haven't gotten into the duality yet. We are still considering standard forms or different forms LPs can take. And so far we have considered the standard form that's called standard form, and later it will also be called so-called primal standard form. So why is it called a primal standard form? Well, if there is a primal, then surprise, surprise, there is a dual. And what is the dual standard form then? So the dual standard form is what I call, and many other people also, is the form of 8.13 here. So it's a minimization problem. So minimized Z, C transpose X. Then there is constraints subject to A is a technology matrix as before, A times X, and now it's bigger than equal to B. And we have sign constraints always. So what is the difference between this dual standard form and the primal standard form? The differences are here. So we are minimizing and not maximizing. And since we are minimizing, it's actually rather natural that we have lower bounds here. So the axes must be bigger than something. Usually if they has to be lower than something, then it kind of implies that, well, taking them to be zero, it's an optimal solution, which is rather boring. Of course, it's not that straightforward, but in general, it's more natural to have, especially if all the numbers are non-negative, this kind of inequality. So just to recall, this is the dual standard form, and then the remark here is what I said. So to compare with this dual standard form like this, then the standard form, let's click here, what we have here is called sometimes a primal standard form. Okay. So these are just two rather simple natural forms an LP can take. And okay, so I haven't given an algorithm how to turn a general form LP into a dual standard form. I think it's not difficult to see how to modify this algorithm 8.10 so that it gives the dual standard form. Let me shortly explain how to do this. So step 1, so this was the standard form or primal standard form transformation. So step 1, you change the minimization into maximization by multiplying by -1. Well, in the dual standard form, it's the other way around. You turn maximization into minimization. And again, the trick to do this is to multiply by -1. Step 2, remove double inequalities. That's the same in the dual standard form transformation also. Step 3, remove lower bounds. Well, obviously in the dual transform you remove the upper bounds. So here it is not from here to here, but the other way around. And again, the trick is to multiply by -1. And step 4, impose sign constraints by splitting decision variables. This is exactly the same. So I hope that the so-called dual standard form transformation, how to do it, should be relatively clear now. So since this is almost the same as the primal standard form, let's not spend too much time on this. Instead, let's go to the final standard form we are considering here, and this is slightly different and maybe a bit surprising and maybe not so easy to motivate at this point, but let's have it anyway. And these are called the slack forms or slack and surplus forms. And what's the rationale, the reason behind these forms? And this is something that, well, these should be the words to live by. Inequalities are nasty and equalities are nice. And this is something that you probably, if you remember your school years and you had to solve an equality or to solve an inequality, somehow the equalities, at least to me, they seem more natural. So what you actually did is, typically you actually solved the equality and then just kept remembering that this is an inequality, and then maybe if you multiply something negative, you have to change the sign in an inequality. Okay. And these inequalities are nasty. This is especially true for computers. So for computers, it's much nicer to check equalities. So that's the rationale behind the slack or slack et surplus, or also called slack or excess forms. So how do we change inequalities to equalities? And this is the rather neat idea here. This is the idea that we will have appearing later also, I believe, that we add decision variables. So in the beginning we have obvious certain decisions we can make, and then we add auxiliary or dummy decision variables. This sometimes makes the problem more convenient. And what are the additional variables we do here? And the basic idea is the following. Suppose that we have an upper bound like this. So this I here is just one row in this LP, so that's one constraint. And we assume that this LP is a standard form. Why not? We know that everything can be written in a standard form, so let's assume that we start with a standard form. And we have an upper bound inequality like this. Indeed, all the inequalities would be upper bound in this case. So here is just formally one line, so AI1 times x1 plus AI2 x2 and so on up to ANI xn is less than equal to BI. Okay, so if this happens to be so that this side is less than equal to this side, then it means that the difference, so the left hand side minus the right hand side, is a positive number, possibly 0. And the thing is that in some sense this is what we choose. When we choose this xi's, x1 up to xn, the decision variables, we implicitly will choose how much slack there is in the constraint. So we can say that this here is the same as, okay, what we have originally, and then in this si, and I have a superscript plus there to denote something that's related to what we had before, so that would be the positive part. Now it's here just to, this plus actually will refer to the fact that we have an inequality like this here. So if this is true, then if I add to this thing here some positive number, I call it Si plus, then it turns out to be equality. Okay. And formally, these are the ones I choose. And not only formally, this is precisely what happens. So if I have to choose x1 up to xn so that this inequality is true, it amounts to choosing those x's and then some positive numbers so that this is actually an equality. That's the same thing. All right. So these Si pluses, they are non-negative. Some people call them dummy decision variables that we can choose. And the inequality constraint becomes an equality constraint. All right. Then a little bit why these pluses here. Sometimes I actually omit this plus, but here I use it to compare the fact that sometimes we can have lower bounds here. For example, in the dual standard form we have lower bounds. And also sometimes it's not kind of convenient or reasonable to turn the LP into a standard form. So in general we have upper bounds and lower bounds. And what happens with the lower bounds? Well, exactly the same thing. We have a dummy variable si, now minus. These are also non-negative, and that's why we have a minus sign here. Okay, so what happened here and what happens here is exactly the same, except that because of this upper bound actually is here a lower bound, then if I take this and subtract something positive, then this will be equality. And this something positive here is again a dummy decision variable that we can choose. So in some sense this Si is the surplus we have in this constraint, or excess, meaning how much this Bi will be exceeded in this inequality. Alright, this was just in some sense this was just a trick. We introduced new variables called slacks and surpluses. Sometimes they are just called slacks. And with that, all our inequalities becomes actually equalities, which is sometimes very nice and very convenient. And then these additional variables, the slacks, actually tell us how much is each inequality, how much there is slack or negative slack surplus. So the interpretation of them is rather obvious. All right. A small comment here. Maybe I should have put this also, emphasize this a remark, but let's have it like this. Maybe it's not. There's no reason to emphasize this more. So in the slack form, what we call a slack form here, all the constraints are equalities, and all the decision variables are restricted in sign to be non-negative. So this is what we insist on the slack form, but not more. So slack form can be either maximization or minimization, for example. Okay, this is pretty much more or less all the freedom we have left. Okay, then important thing, any LP can be written in a slack form, and how to do it, this is not difficult. Actually, this is formally very easy, although sometimes writing it down is probably a bit tedious. So how do you do it? So you introduce for each inequality constraint. This is important. So you have an inequality constraint number I. For each of them, you introduce a unique slack or surplus variable. So xi plus or xi minus, as explained above. And okay, I do not give an explicit algorithm here. I think that would be a bit of an overkill. Let's just look at an example and see how this goes. This shouldn't be too difficult. I think this is the easiest transformation we have. So here is the example 8.15. I call this slack form transformation. So let's consider the following LP. So this is the LP we have. We have a minimization of this kind. Then we have a subject to two constraints. We have a lower bound like this and upper bound like this. Then we have that x1 and x2. They have sign constraints, so they are positive or non-negative. That's nice. And then we have this anti-constraint here, if you like, that x3 is actually unrestricted in sign. Just to emphasize that x3 is not appearing here in the sign constraints. Okay, so this is what we want to transform into a slack form. So what is the point of the slack form, or the goal of the slack form? We want to have all the constraints equalities, and we want to have sign constraints for all the variables. So therefore, this minimization is fine by us. Of course, we can turn it to maximization if we like. No problem there, but we don't have to. Okay. So, what has to be done? Well, one thing that has to be done is to put this x3, split it into positive and negative part. And this is what I do next in the first step. I could have started by introducing the slacks and surpluses also. I mean, usually, well, sometimes the order of these algorithms is not important, and in this case, that's so. So let us just start by splitting this x3. And how do I do it? Okay, remember x3 becomes x3 plus and x3 minus everywhere, such that x3 is the positive part x3 plus minus the negative part x3 minus. So let's see how this works. So here in the top, it's the x3 here, so I have to replace this by 7 times x3 plus minus x3 minus in the parentheses, and then I open the parentheses, so it becomes this one here. And then I have to do it for all the, well, wherever x3 appears. And I do it. I have it in parentheses, then I open the parentheses and adjust these columns so that this is an x1 column, x2 column, x3 plus column, and x3 minus column. So this is what happens here. And then finally, now x1, x2, non-negative or positive, I have x1, x2, x3 minus and x3 plus, non-negative. And this additional anti-constraint is not there. Okay, that was the point. So what happened here? I simply impose the sign constraints everywhere. So basically I split x3 into positive and negative part. Okay, so what is left? We have to turn inequalities into equalities. And how do we do this? Well, here you see I have upper bound here, meaning that I have a surplus here, so this will be minus s and 1 now minus, because this is the first constraint. And here I have an upper bound, and this is the second constraint, so it will be s2, and I use the superscript plus to denote that this is a slack. And yes, this is what happened next. So from this to this, if you see, everything else is here kind of the same, except that now I have an additional variable here. Since it's the upper bound, it's minus, so this minus here is corresponds to this minus here in the superscript. So that's the surplus related to this first constraint, so that's why it's called S1 and minus because it's surplus. And in the second constraint we have S2, 2 because it's the second constraint, and plus because it's a slack. So this plus and this plus correspond to the fact that it's an upper bound. And then additionally, now it's good to note here that actually now we have 6 decision variables. So we started with 3, then we got 4 because the third one was split into the negative and positive part, and then still 2 more because we needed to turn the inequalities into equalities. And note that here in the objective function the slacks are never explicit, but they are there of course. For example, when you want to implement this to Octave, you have to understand that this is plus 0 times S1 minus plus 0 times S2 plus. Alright, so this is how we get a slack form. And yes, I do realize that at this point it's still a bit vague. Why do we want to do something like that? But I hope it becomes relatively clear, relatively soon. Okay. More about slack forms. So 8.16 remark. Okay, this is a very homebrewed definition, pure slack form. I don't think this appears, this terminology, anywhere else. Here it is just, well, I needed a name for this concept, so I could have called it basically anything, of course, so I decided to call it the pure slack form. And what do I mean by this? So sometimes, it's sometimes maybe undesirable that we have these slacks and surpluses, slacks and excesses, these plus and minuses. So that in some line the slack variable is plus sign and sometimes the minus sign. Maybe it would be, sometimes it would be nicer just have plus signs. And is it possible? Well, indeed it is possible, and how to do it, it's relatively straightforward. We only need to have this kind of upper bound inequalities, so not these at all. And how do we do that? Well, we could, for example, start with the primal standard form. And indeed, here is a little bit of matrix notation for you. If you are familiar or comfortable with this notation, I think this kind of sums up things rather nicely. But if you are not comfortable with block matrix notation, then I hope that you will soon become comfortable. We will do this in this course a lot. And this also is some kind of, now a bit late, I suppose, motivation. Why did we consider block matrices before? So, what's going on here? So we only have positive slacks. So let me now suppress the notation, the superscript plus here. So SI will be the slack associated with constraint I, and there will be plus sign there. So there are no surplus variables at all. And formally, if I start with this kind of LP, okay, you should be, a simple human pattern recognition by now should tell you that this is a standard LP form. So how do I write this in slack form? And the idea is that, okay, in the slack form I have these dummy variables, S1, S2 and so on for each row. So now I have an extended decision variable, or extended decision variables. I have first the X is the original decision variables, then the S is the slacks. And let me just put them together. Well, actually not this way, but this way. So I have big or tall column vector for the decision variables. First I have the X's and then I have the S's. And well, this is what is written here. So what I do have then the coefficients for the maximization, the C's. Well, okay, this should be a row vector here. So first I have the C's transposed, so this is the row. So these correspond to X's, and then for the slacks, okay, they don't appear as such in the objective. So what does it mean? Because we need to have these vector dimensions correct. It means that they appear there as zeros. So there's some amount of zeros there. So the new objective vector is here. So this is the row of C's, and then again 0 will be the column vector of zeros with appropriate dimensions, so it transposes the row vector of zeros. So this here will be our objective. So that will, in here it will denote this. So there are C's, 8, minus 8, 7, minus 7, and then 0 and 0. All right. What about the technology matrix? What happens here? So these inequalities, they become equalities. Of course, that's the whole point. This is what we want to do. And now the new decision is of course x and s, so we have this enhanced or extended decision variables. So what's the matrix? What's the technology matrix now? And this is not difficult to see either. So it will be the original one, and then I append to the right an identity matrix. So you can probably see it here. So the original one is here. This is the A, and this is, as you can see here, only with 2. Okay, there is the minus here, but now we have this plus version, so these are pluses. So I have here the coefficients 1 and 1 and 0 and 0. And indeed the slack variable is unique to each row, so it will be introduced to that row, meaning that constraint, and not to the other ones. And if you start doing this, you end up building diagonal ones and everywhere else zeros, and this is of course what we call the identity matrix. So indeed, what happens that the constraints become like this. So there is this original one A, which corresponds here, it's multiplied with x's, and then the slacks will appear in this table after the a's and x's, which means that then there will be I multiplied with s. And formally it means that this big block matrix is multiplied with this long decision vector. And this has to be B. And finally, of course, we have the sign constraints. So if you are comfortable with matrix notation, and you should get comfortable because this is something that you can do very neatly, very simply, in a very simple manner with Octave. So if you have a standard form LP, then to make a slack form out of it is very simple. Just do it like this. All right. So then we have left a couple of exercises for this this section. Let me shortly go through them and see if I give some very minor hints. So 8.17 exercise, well, primal standard form, dual standard form, and slack form. So here we have to consider an LP. I've given this LP as a more or less as a mess, well, meaning that it's pretty far from any standard form for the sake of exercise, of course. And now this LP you have to express in the primal standard form, dual standard form, and slack form. Okay, this is the first part of this exercise. Notice this. And then the second part is that you have to solve all these different form LPs. So you will get 3 different LPs, or LPs that look different, of course. The whole point is that they are actually the same problem, same LP in some sense, or equivalent. And then you have to solve all these different LPs with GLPK. And then, yes, check your results. In some sense, you should get the same results because they are the same problem. If you don't, then either you made some mistake or there's something interesting going on. Or both. Okay. What about the hints? You can do this either by being clever or being just following the rules. Being clever, you might figure out some easy cheat tricks to make the transformation. That's fine. I actually encourage you to be clever. But clever people usually make mistakes. Yes? So it may be useful or a good idea that you start doing this the way I kind of intended. So you start with one primal standard form, and you will just look at this and follow the algorithm 8.10, if I remember correctly. Let me check whether I remember. Yes, 8.10. So go to this algorithm, follow it precisely. And after you have done that, you have gotten this thing here into a standard form. All right. Then from a standard form to a dual standard form, step one is probably the one where you have to do most of the work. Step two, you don't have to do much here, really. Once you have the primal standard form, the dual standard form you get it pretty quickly. And also finally, the Slack form, you will get it. I think that from the primal standard form is relatively straightforward how to do the Slack form. Okay, it might be also a good idea to do the Slack form directly to this form, because the Slack you will need equalities, and in this you see that you have already an equality here, so you don't need Slack. And so it happens, you will notice that the Slack form is not unique. So if you start with this, you will only have 2 Slacks. Or 3 actually. And if you start with this primal standard form, you may probably have a different amount of Slacks. But of course these forms are somehow, you can have even in different standard forms. Obviously you can change the order of constraints, for example. If I change this constraint to the first one, of course the LP is the same. Okay, and then yes, you have to solve these all different forms with GLPK. This is again maybe a little bit of hard work. You have 3 LPs to be solved with GLPK, but copy paste will be your friend here. So it's not that much if you work efficiently, but if you don't, at least you get the exercise. So sometimes it pays to be not so efficient in doing the solutions, because once you make mistakes and type everything down from the scratch, it means that you will usually learn more. All right, and then a final exercise of this section is the exercise 8.18, and so now we have had 3 kinds of standard forms. Let's have more. The more the standards, the merrier. So this is what I call, or actually what GLPK calls standard form. So GLPK standard form. And this is yet a different thing. And this is, it's sometimes convenient. If you remember, it's rather boring with GLPK. We always had to put as lower bounds empty matrix, upper bounds empty matrix, and then a C-type and var-type and sense and so on. All of this clutter. And why it's kind of boring or frustrating is that if you think about the LPs, the basic data in LP always just C, A, and B. So the objective, technology, and resources, if you want to call them like that. And for example, if we assume a standard form, then this fixes it. Now you can actually call GLPK with only these 3 parameters, C, A, and B, and not give anything else. And then GLPK will assume that rest of the parameters to be such that it's actually what it calls a standard form. But unfortunately for us, the GLPK standard form is the following, 8.19. So if you just call GLPK with parameters C, A, and B, it assumes that it's a minimization and the constraints are actually equalities. And sign constraints, the x's are positive. Okay, there is no standard. What is standard? So apparently those who developed GLPK or at least made the incorporated it to Octave thought that this would be a nice standard form. Okay, I don't completely agree with them, but actually I see where this is coming from, or I know where this is coming from, so it is in some sense natural. Nevertheless, it is what it is. And then you may think that maybe it's convenient to use GLPK so that you transform everything first into this kind of form, and then you don't have to give anything else to GLPK. And this is indeed the point of this exercise. So you take the LP 8.7 from problem 8.6. Let's look at what it is. It's this. So it was given in a very non-standard form, and this is what we showed, how to put this in the standard form, or the primal standard form, or the standard form of these nodes. Now the problem or exercise here is to take the very same LP and transform it into this, what is called GLPK standard form. And then to check that you actually have done it, it is the last part of this exercise is to solve the LP 8.7 with GLPK by using only these three input arguments. Okay, so that was all about different standard forms. This was kind of technical, and some of the points why do we do something like this may be at this point a bit unclear. Sorry about that, but already in the next section, when we call to duality, we will see why these different forms are useful. And this is also well, obviously this part on the standard forms was to prepare us for the concept of duality. So that will be the topic of next video lectures. See you there. Bye bye.